So at the beginning of class on Wednesday, I'll give you a 15-minute quiz. It will focus on, just so you know, I'll tell you right now, right, quiz 1, which is, like I said, next class, will focus on graphing angles, which we did a little bit last time, and we'll do more today, and also coterminal angles. Okay? For a second I thought someone threw something at me. Like, it's not that bad, guys. So I haven't talked about coterminal angles at all. I'll get to that today. Hopefully it's a straightforward idea. We did talk about graphing angles, and I'll do more again today. But these, your 4 questions on Wednesday, will be of this type. So you're not too scared. So let's just go through and review a little bit. What's an angle? Right, so an angle is formed by 2 rays, right? So if I draw 2 rays, boom, 1 ray, boom, 2 rays. Is that an angle? Does that uniquely identify an angle right now? Close. I'm glad you're confident. This doesn't identify a single angle, because you could be talking about rotating from this ray to this ray, or from this ray to this ray, or from this ray to this ray, right? You need to give me some sort of a rotation. An angle is a rotation. Okay? So to specify specifically which angle you mean here, you have to put a little arrow. Like this part, rotating from this initial ray to this terminal ray, is an angle. Okay. If I draw the exact 2 same rays, but I put this rotation, that's a different angle. So with 2 rays, you can form a bunch of different angles. In fact, you can form an infinite number of angles between 2 rays. Because you can go around and around and around and around, and that would be a different angle. These 2 angles, I haven't talked about this yet, but we're going to talk about it today. This angle and this angle are what's called coterminal. Why are these 2 coterminal? It ends at the same place on both of them, right? This is the terminal ray here. I mean, first of all, they have the same initial and terminal ray, but they end on the same ray here, and they end on and this ends on the same ray. This guy would not be coterminal because it starts and ends on a different ray. But we'll talk more about that in a minute. I also talked about standard position. What's standard position? When the initial ray is on the positive x-axis, your angle is said to be in standard position. So here's 2 angles in standard position. I need a positive x-axis to be in standard position. So here's my initial ray, terminal ray, angle, standard position. Now, I was going to draw another one. I guess I will. So I could also put, this could stay in standard position, but I could identify this rotation, and that would be a different angle. This would be angle 1. This would be angle 2. If you remember from last time, there's a difference in the measurement of these 2 angles. There's two common units we use to measure angles. What are the 2 units of measure for angles? Radians and degrees, right? We talked about this a little bit last time. We said a complete rotation, right, from one ray back onto itself is 360 degrees. Or a complete rotation of one ray back onto itself is 2 pi radians. As far as measurement goes, what's the main difference between this purple angle here and this blue angle here?
It's positive.
One's positive and one's negative. So how do you tell when an angle is positive and when an angle is negative?
Positive is counterclockwise and negative is counterclockwise.
Right, right. So positive angles rotate upward first if they're in standard position. Negative angles in standard position rotate downward first. So angle 2 here would be a negative angle. Whether it's in degrees or radians, it's still going to be negative because it's rotating down first. And angle 1 here would be positive. All right, so let me draw you some usual angles that you run into. This is kind of meant to go with this definition in this example here, but I'm just kind of making stuff up. So go with it. So here's a couple angles that you'll probably run into in your life in this class. The angle that starts on the positive x-axis and cuts the first quadrant in half, going this way. I want you to tell me what the measurement of this angle is in both degrees and radians. 45 degrees. Right, this is 45 degrees. How do you know that? Because I took a 90-degree angle, right, between the positive x-axis and the positive y-axis is a right angle, a 90-degree angle, and I cut it directly in half. So that has to be 45 degrees. What about in radians?
Pi over 4.
Pi over 4. Why?
45 degrees is one-fourth of a...
Right, so you've taken 1/4 of this half rotation on top. Right, if you look at this half rotation here, from here to here, that's pi. How do I know that's pi? 2 pi is a full rotation, so you go half a rotation, that's pi. And then what you have to, if you're trying to figure out the measurement of this angle in radians, you have to figure out how many slices have I gone out of this full pi. Well, I've cut the pi into 4 equal sections. 1, 2, there'd be another one here and another one here. Right? If I split this quadrant in half, there'd be 1, 2, 3, 4 sections. So this angle cuts my pi into 4 equal sectors. That's why in radians, this angle is called pi over 4. What about let's see, maybe I go out here like this, and I put another one here. Right, and I tell you that these are equal sectors, so these are supposed to be 1, 2, 3 equal sectors. I want to know what this measurement is in degrees and radians. 60 degrees, I hear. 120 degrees. Right, because I went too far for 60. Right? So this is actually 120 degrees. And what is it in radians?
2 pi over 3.
2 pi over 3. I like the 2 pi over 3 better because it's kind of more obvious. Well, not more obvious, but obvious enough. Why is this measurement 2 pi over 3?
2/3 of a pi.
It's 2/3 of a pi, right? I mean, if you take your half circle, which is pi, this guy's pi, you've cut it into 1, 2, 3 equal sections. How many of them have you gone? 2. So let's see. How are you feeling that third grade? That's okay. I put a remark up here. Note that when we assign a variable to an angle measure, we usually use Greek letters. So these angles you know, right? Because I broke pi into 4 equal sectors, so you know this measurement is pi over 4. But if I just randomly draw 2 rays, right? I'll put my first ray on the positive x-axis, but then I'll just make some random ray down here. I might not have any idea what this angle measure is. Normally, when you don't know what something is, it's a variable, right? And usually we call variables x, maybe y. Okay? But in angles, for some reason, I don't know when it started. I don't know, maybe because the Greeks really liked angles. But we usually use Greek letters for variable angle names. So we'll call this theta usually. Right? T-H-E-T-A, theta, Greek T. Instead of x or y. Right? It's a variable quantity that's an angle. Alpha, beta, gamma, those are other possible angle names. There's nothing really to learn here. It's just that instead of using x and y, we start using Greek letters for angles. Okay. Now you'll see we were able to think and figure out measurements in both degrees and radians for this angle and for this angle. Okay. There's a formula that will allow you to go between radians and degrees whenever you want. Personally, I don't find this formula super helpful. I think what it allows students to do is be lazy and not learn what I want them to learn. Okay, because students will, if I give them an angle in radians, they'll convert it to degrees first and then graph it, instead of just working in radians. You can do that. All right, it's not going to kill you, but I encourage you strongly to start thinking in radians, okay? Because it's going to come up all the time, and you're really not going to want to waste the time to convert everything to degrees first. That being said, I'm still going to show you how to use this formula because it does come in handy in different classes. In this class, not so much, because I want you to always think in radians. I put 4 examples here. I probably won't do them all. Well, let's look at a couple of these. Convert the following angle measure from degrees to radians or radians to degrees as necessary. Hopefully you know what 90 degrees is in radians. Hopefully. Some of you. You know what 90 degrees is in radians? Pi over 2. Okay, good. So we don't have to actually do any work here. Right? But if I wanted to use this idea, the formula up there says pi radians equals 180 degrees. It's not actually a formula, it's more giving you a 1 you can multiply by. It's allowing you to use dimensional analysis. Okay? So if I wanted to convert this showing some sort of work without just looking at the picture, I would take 90 degrees and say, okay, I'm going to multiply by something that equals 1. And in that fraction that equals 1, I'm going to put degrees in the bottom and radians in the top. So I'm multiplying this. And what's going to happen is the degree unit is going to cancel out the degree unit in the bottom and leave me with radians. This is dimensional analysis. Maybe you've seen this in another class. But I need to pick a unit fraction here, something that equals 1. So what I do is I put 180 radians on top. Oh, I'm sorry. I could do that. That would be foolish. I put pi radians on top and I put 180 degrees on bottom. Right? Because pi radians is equal to 180 degrees. So I'm just multiplying by 1. What that allows me to do, though, is cancel out these degrees because one's on top, one's on bottom. So I cancel. And it leaves me with just the unit radians. So altogether, if I think of this as 90 over 1 and multiply straight across, I get 90 times pi over 180. Degrees is gone because the unit canceled. And then I just reduce. 90 on top, 180 on bottom, leaves me with a 1 over 2. So this is pi over 2. Which is what we got. Now, remember I said sometimes we drop radians. I did it without even thinking. Right? Because there was no degree symbol, I assume this was radians. But if you're going to be super meticulous, which is an okay quality, put radians on the end so I know what measurement you're dealing with. So that's how you can convert between radians and degrees, or at least between degrees and radians is what I did. Not super useful in this class, but one day might be. What about negative 150 degrees? How would I convert this to radians?
Same way.
Same exact way. If you start with degrees, you can always convert to radians by multiplying by this unit fraction, pi over 180. Just do it. Pi radians on top, 180 degrees on bottom. Units cancel, leaving me with just radians on top. Think about this as over 1 and multiply straight across. I forgot something. What did I forget?
Negative.
Oh, good. I thought you were going to say radians. I did forget the negative sign, right? But I might as well also put radians here, so we can be meticulous. Now, I would not leave the answer like that. That would irritate the poop out of me. What should I do? Reduces, right? Certainly, if nothing else, there's a 10 in both of them. Right? 15 over 18, what? 3 goes into both of those? So let's see, this will be 5.
5, 6.
So it looks like 5 pi over 6, negative. Oops. Even though I said it. And I won't write the radians. Again, if there's no degree symbol, you assume radians. What do you think changes if I go the other way? Let's skip to D. 1, 2, skip with you. 99, D.
Look at the radians on the bottom.
Right, so now I'm starting in radians. It's not written, but it's assumed. I'm starting in radians, which means when I multiply, I need to cancel the radians out, so I better put radians on the bottom. Therefore, degrees is on top. Fair enough. My unit fraction here puts a pi on the bottom and a 180 on top, because pi radians is equal to 180 degrees. And then I do my magic. Radians on top, radians on bottom, gone. Actually, there's a pi on top and a pi on bottom as well, right? So I might as well get rid of that at the same time. Now, personally, I wouldn't do more work than I had to, and I have a pretty good grasp at multiplying fractions. So I would say, well, this 3 and this 180 can reduce right now, giving me 60 degrees up here. So really all I have to do is multiply 17 times 60 degrees. 600 plus 420, 1,020 degrees. So I did some fancy fraction work there, which just consisted of reducing this. Yes, miss?
Would 5 2/3 pi would that be okay?
5 2/3 pi is equivalent, but it's not in degrees. So since the problem's asking us to convert to a different measurement, that would not be the correct answer. Right, so you can make this a mixed number, and a lot of times I like the mixed number better because it's easier to graph. Right, 3 goes into 17 5 times with 2/3 left over. But this is still in radians. So we're still going to have to get to here before we've completed the instructions which say convert. Okay, sweet. So now I go in and I take a little time to show you how to graph in radians. We talked about this already, so I'm going to go a little faster than I normally would. Okay. But I am going to say more about this because I've just found it as a weakness. Okay, people have a hard time graphing in radians. So, let's do it. So if you want to graph, for example, any multiple of pi over 4. So when I say multiples of pi over 4, what does that mean? What's a multiple of pi over 4? 3 pi over 4, 7 pi over 4, 800 pi over 4. Right? Any number of pi's over 4. If you want to graph a multiple of pi over 4, you have to start by splitting pi into 4 equal sectors. This is what we talked about. Here's how to graph multiples of pi over 4. So we start by taking pi, which is a half circle, right? half of a full rotation, that's pi. And you break that into 4 equal sectors. Because we're dealing with pi over 4, this tells you the number of equal sectors, the denominator. So if I were dealing with multiples of pi over 6, I would break this half rotation into 6 equal sectors, right? So now I do this. 1, 2, 3. Because this is an even number, right? It's a 4. So if this is a 4 or a 6 or an 8, any even number denominator, you're going to use the y-axis when you break things up. If this were like a pi over 3 or a pi over 5, you would not use the y-axis. Let me show you. And so sort of in an alternate universe, maybe you hate 4. We want to do pi over 5. If you want to graph multiples of pi over 5, like 2 pi over 5, 3 pi over 5, etc., you'll start with pi, which is a half rotation, and you'll break it into 5 equal sectors. But if you're going to break this half rotation into 5 equal sectors, you're not going to land here. Okay? Because this is half of my half rotation. So the way I think about it is, if I have to break this into 5 equal sectors, then I have to break this into 2.5 sectors. Which means I don't land on this one because it's halfway in between a sector. So I would go maybe 1, 2, and then a half of a sector. And then if I mirror that on the other side, I get 1, 2, 3, 4, 5 sectors. So if you have an odd denominator, you will not land on this y-axis here. It's just the way it works out when you split it up. If you have an even, you will always land on this y-axis for one of your breaking points. Of course, this is only going to allow me to graph the first 4 multiples of pi over 4. 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. What if I wanted 5 pi over 4 or 6 pi over 4? You'd have to keep going. Here's your second pi underneath. And if you break that into 4 equal sectors, and keep the count going, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4. So this is the diagram you need, and this is the diagram I want you to show me, if you're trying to graph pi over 4s. So for example, graph 7 pi over 4. You would start by taking your circle, breaking the top half into 4 sectors, breaking the bottom half into 4 sectors. Right? You're breaking everything into 4 sectors because that's the denominator. The 7 here tells you how far to count. Right? Start from the positive x-axis. Why am I going to start from the positive x-axis? That's standard position. That's what we agreed on. That's the best place to start graphing for us. So you start from the positive x-axis and go 1, 2, 3, 4, 5, 6, 7 sectors. So this angle here is 7 pi over 4. Right? You need the arrow because it shows me the rotation, which is what the angle actually is. What if I made it negative? How would you graph negative 3 pi over 4? Count 3 in the other direction. It's still over 4. The denominator is still the same, so you still have the same picture in your head, the same diagram of 4 equal sectors on the bottom, 4 equal sectors on the top. But now, because it's a negative out in front, you start counting this direction. 1, 2, 3. So this angle going this direction is negative 3 pi. All right, I'm going to give you something outrageous now. Graph 63 pi over 5. What's the strategy? Cry a little, die a little bit inside.
I assume it's, when you go all the way around, it's 10, so just do that 6 times and then 1, 2, 3.
Right, so the brute force method, which is not what she is saying, although similar, the brute force method would just be to start going and count 63 times, right? And when you get to 63, that's 63 pi over 5. Okay. A little bit kind of smoother method, which is halfway, which is a little bit of an extension of what was suggested. Think of this as a mixed number. Right? How many times is 5 going to 63? 12 times, with a remainder of 3. So you can go 12 pi and then 3/5 pi. Each of those in itself is pretty easy to do. Where would 12 pi land you?
6 revolutions.
6 revolutions. Where does 2 pi land you? Right, if I start here and I go around 1 revolution, that's 2 pi, right? And if I go around another revolution, 4 pi, because I went another 2 pi. 6 pi, 8 pi, 10 pi, 12 pi, so I got this part. Then how far do I go? 3/5, 3 out of 5 pi's. 1, 2, 3. Right to here. So that's my answer. All right, this swirly whoop-de-woo thing here. This is 63, that's the technical term. 63 pi over 5. I have an answer.
Will we be getting any questions like that
Yes.
on our test?
Sure.
If we do like nice circles,
What's wrong?
yeah.
Will you be getting any questions like this on your test? Certainly, you will be getting things that go over 2 pi. Okay, so you will definitely have to do more than 1 revolution. Whether I'm going to make you do 6 revolutions or 20 revolutions, that's starting to become a pain in my butt, right? Because then I have to count to make sure you did the right number of revolutions. So, but definitely be ready to do things over 2 pi. The world doesn't stop at 2 pi. It keeps going. In fact, if you just drew for me, if I told you to graph 63 pi over 5, and you came over here, and you split your pi into 5 equal sectors, all right, you drew this for me, and then you drew this angle, would I give you full credit for that? No. First of all, there's no indication of rotation at all. Right? If you don't have a little arrow here showing you the rotation, you're not graphing an angle. Right? You're graphing rays, which is great, but not what I want. Right? So first of all, you definitely need to show me the rotation. What if you did this? Would that be okay? No, because that's 3 pi over 5. I understand that 3 pi over 5 is related to 63 pi over 5, but that is not what I want. Right? I want you to do your 6 revolutions and then go 3 pi over 5. So this is not 63 pi over 5. It's a good start, but it's not. So that's graphing in radians. What do you think? It's fine? Cool. Good. I'm happy. On to the next.
That took a minute to get in the notes.
Oh, I bet. Okay. So one of the tricky concepts I've found is this exact same concept that we're talking about right here. Okay? Even though two angles may start and stop at the same place, like 63 pi over 5 and 3 pi over 5, they are not technically the same angle. Right? They have different amounts of rotation, so they're different angles. This is, to sort of talk about this idea, we introduced the term coterminal angles. So two angles in standard position that share the same terminal side are called coterminal. You'll notice a sort of pattern between all coterminal angles. This is the remark.
What do you mean by sharing the same terminal side?
So the terminal side of an angle is a ray, right? So what I mean is they end at the same ray.
So, like that example?
This ray and this ray are the same ray,
Okay.
right? Because they're pointing in the same direction. So two angles that end at the same ray, end at the exact same place, are coterminal.
Okay.
The pattern for all coterminal angles, for the measurement of all coterminal angles, is that they're either going to be off by 360 degrees, or a multiple of 360 degrees, or they're going to be off by a multiple of 2 pi. So this is the remark that I said up here. If an angle measures theta degrees, then any angle coterminal to that angle will measure theta plus k times 360 degrees. Let me draw a picture. Here's your angle. It's a variable. I don't know what it is. It looks like 45 degrees. It's not. Theta degrees. So this is a variable, right? Theta. What I'm saying is if you draw me a coterminal angle to theta, the measurement of the coterminal angle is going to follow the formula theta plus k times 360 degrees. So suppose I want another angle that ends at the same ray as theta does. So here's one. It's not the same angle because it's got an extra full rotation. Right? It's got one full rotation and then it goes theta degrees. So my question is, what's the measure of this angle?
Theta plus 360.
Theta, right? Because of this little portion right here. This little portion of the rotation is theta degrees. Plus it has a full rotation before you get to that. And we know a full rotation in degrees is 360 degrees. I put a 1 there to make it fit this format that I put in the notes. Right? All coterminal angles in degrees have measurements that look like the original degree plus a multiple, a constant multiple, times 360 degrees. So if you go around one extra revolution before you get to the same ending point, it'll be theta plus 1 times 360 degrees. This part here counts revolutions. So another example might be if I decide to start here at the positive x-axis, go around once, twice, and then end at the same place. What would the measurement of this green angle be?
Theta plus 2.
Theta plus 2 times 360. So for example, if I knew theta was 40 degrees, then I could calculate this by doing 40 degrees plus 720 degrees, 760 degrees. Okay, this is the general format here.
I'm confused by that, because it looks like it's the same exact thing as theta plus 1. Visually, it looks like the same.
Yeah, I think it's actually a rotation.
It's got an extra rotation in it though.
Yeah.
So it's doing it twice then?
Yeah, right? Count. 1, 2. Or the black one doesn't have this inner rotation part.
Oh,
Right, the black one started here. 1.
oh.
What if I went the other way? What happens if I go backward? Yeah, so if I, say, start here, and then go back this way, this will measure theta degrees minus 1 times 360. Why? How do you get that? I have bad hearing. It's going backwards. Oh, okay. Yeah. It's going backwards. But it's a little trickier than that, right? Because actually what happened here, let me draw another picture so I don't mess this one up too much. This was my theta. The way theta minus 1 times 360 works is it goes theta first, and then it minuses a full revolution. So if you're counting in your head what theta minus 1 times 360 means, it means go this way, but then go back on yourself. Now we don't ever draw this because this cancels out. But as far as logically what theta minus 1 times 360 means, is it means go theta, which is this, but then go backward 360. So this is a little theta in here, and then this went minus 360 to end me at this terminal right. If I wanted this in radians instead of degrees, suppose I had theta radians, and I went 1 revolution first, and then I landed at the same place, so looking at the black arrow, what would I be in radians? What's 1 full revolution in radians? 2 pi. 2 pi. So in radians, you have to add 2 pi to get that extra revolution. What about, so that was the black guy who had 1 extra revolution. What about the green guy that has 2 extra revolutions?
So we theta plus 1 times 2.
So this would be theta plus 2 times 2 pi, right? This is counting the number of revolutions. Or that would be kind of silly. You'd usually just write 4 pi is 2 times 2 pi. 2 times 2 pi is 4. And this guy here, the blue one, would be theta minus 2. Let me do some concrete examples for you without these thetas, actual numbers. Okay, so the example here, for each angle measure, graph the angle in standard position, then find and graph 2 angles coterminal to the original. So I'm giving you 120 degrees as my measurement. I want you to graph that angle and then 2 coterminal angles. And I also want their measurements when we find the 2 coterminal. So first of all, how would I graph 120 degrees?
It's 30 degrees more than 90 degrees.
Yeah, so when graphing degrees, I would compare things to the axes. Right? You know this is 90 degrees, you know this is 180 degrees. So if you want to graph 120 degrees, you have to go 90, but then a little bit more. Okay, so I put this guy over here. 120. It doesn't have to be perfect. Okay, I'm not going to get my protractor out and try to catch you slipping. But it's got to be in the right quadrant, you know what I mean? And it's got to be, like for example, is 120 going to be closer to the y-axis or the x-axis in y? To the y-axis, right? Because you only went 30 degrees out of 90. So I want you closer to the correct axis. But otherwise, we're not going to make a big deal out of it. Coterminal. So give me an angle that is coterminal to 120 degrees. Give me an angle measurement. How'd you get that? Add 360, right? If you add 360 to this, you'll get a coterminal angle. You won't need to draw any new rays to draw it. Right? The coterminal angle of 480 degrees starts here and ends at the exact same place. And we got that by taking my original and adding 360. So that's how you get coterminal angles. I wanted 2. Give me a negative coterminal angle.
Negative 240.
How'd you get that?
Subtract 360.
Subtract 360, right? I'm not blowing any minds yet. So if I subtract 360, it'll give me this angle. It'll be negative 240 degrees for the measurement. And we get that by doing 120 minus 360. This, yeah, both of these are coterminal. This would be a positive coterminal. This would be a negative coterminal. Right, I can be kind of tricky with this, not too tricky, but I could ask, let's do a bonus part here. I want a coterminal angle to 120 degrees. So find an angle coterminal to 120 degrees. That is bigger than, oh, let's say 1,080 degrees. So how do you accommodate me here?
You could multiply 360 and over 1,000 degrees and then add another 120.
Right. 480 is not big enough, right, to answer this question. If I want a coterminal angle that is bigger than 1,080 degrees, 480 is not enough. So just keep going. Right? Keep going until you get one that's big enough. The most brute force, straightforward way to do that is to keep calculating it every time. Right? If you go 1 revolution, it's 480. If you go 2 revolutions first, what would that angle be? You'd have to do 120 plus 2 times 360, because you went 2 extra revolutions. So 720 plus 120, 840. Big enough? No, but another 360 should do it. Right? So if you go 3 revolutions first, that should, because if you add 360 to this, you get something bigger than 1080. Right? So if you do 1, 2, 3, and then go back here, I know that's garbage. Don't try to copy. But if you do 3 revolutions first, then you would do 120 plus 3 times 360. So this is already 1080, right? 3 times 360 is 1080. So then you'll do another 120, 1,200 degrees. This would answer the bonus question because it's bigger than 1080. In fact, there are multiple answers to this question because I didn't give you an upper bound. I didn't say bigger than 1080 but less than, 1,400 or something like that. I just gave you a lower bound. So in fact, you could add another 360 and that would still be coterminal and bigger than 1080. The quicker way to do this, which was pointed out originally, is to take 360 and divide it into the number you're trying to get bigger than. Right? You're trying to go bigger than 1080, so divide 360 into 1080 first. You know it goes in 3 times. So that means you're going to have to take an extra 3 revolutions past your original angle. Questions about that? Give me an example of radians. So same instructions, but now I'm giving you an angle measurement in radians. Right? Take the angle 12 pi over 5, find me 2 coterminal angles and graph it. So first off, how am I even going to graph 12 pi over 5? Yeah, so you got to do a couple things. Right? Certainly you're going to have to divide your pi up into 5 equal sectors. Maybe the top pi and the bottom pi, but at least the top pi. So maybe there's 1, 2, 3, 4, 5. Now, because this is bigger than 2 pi, I would go ahead and change it into a mixed number first. How do I know this is bigger than 2 pi? Yeah, because if you double 5, 5 times 2 is 10. So I know I've gone more than 2 pi, because 12 is bigger than 10. So in that instance, I know I've gone around more than once, so I might as well change this into a mixed number. This is equal to 2 and 2/5 pi. Using a mixed number is very helpful, I think, but sometimes it does confuse people because they think that 2 pi means you go around twice. 2 pi does not mean you go around twice, right? Because pi is only half a circle. Right? Pi is out here. So 2 pi means you start from the x-axis and go back to the x-axis with 1 revolution. There's 2 pi. But I actually want to graph an extra 2/5 on top of that. So I keep going to right here. So this ray would be the ray that lands at 12 pi over 5 with an extra revolution before. Okay. Talk to me about coterminal angles. Give me an angle coterminal with 12 pi over 5. 22 pi over 5. How'd you get that?
I added 2 pi too.
You can add 2, right. Since we're dealing with radians, one way to get a coterminal angle is to just go an extra revolution. So start at the same starting place, go around once, but then go around an extra time and figure out what that new rotation, what that new radian measure is. You had 12 pi over 5, that's what you started with, plus 1 full rotation. So this is what you would have to calculate. And this is just like adding fractions back in, I don't know, what grade do you learn adding fractions? Whatever grade. Right, this is 12 over 5 plus 2 over 1. Ignore the pi's. I mean, they're there, but they don't change the mechanics. All right, multiply this by 5 to get a common denominator. So this will be 12 pi over 5 plus 10 pi over 5, which is 22 pi. This is a coterminal angle to 12 pi. No doubt you'll be thinking in your head, do I have to show all this work? That's how I always get that question all the time. Do I have to show all this work? Hopefully you get to a point where you start seeing 2 pi as multiple fractions. 2 pi is 10 pi over 5, right? Because 10 over 5 is 2. 2 pi is 8 pi over 4. 2 pi is 20 pi over 10, right? So all I'm doing here is saying, well, I know 2 pi is 10 pi over 5. So I just add 12 plus 10 to get my 22. Done. You could do this with mixed numbers. In this particular case, if you really wanted to, you could take 2 and 2/5 pi and add 2 pi. What would you get? 4 and 2/5 pi, right? I mean, you just add 2 and 2/5 pi plus 2 pi. This whole number and this whole number will add to give you 4 and 2/5 pi. And you can check and make sure this is the same thing. Right? 4 times 5 is 20, plus 2 is 22, so it's the same thing. You have to be a little bit careful with this when you go from positive to negative or from negative to positive when you switch signs. Let me show you what I mean. We answered part of the question, right? The whole question here was to find me 2 coterminal angles. You found me 1. Bravo. Find me a negative coterminal angle now. So pi over 5, or even 2 pi over 5, is not negative. So that can't be a negative coterminal. 2 pi over 5 would be a coterminal angle, but it wouldn't be a negative coterminal angle. So if I ask specifically for a negative coterminal angle, let me redraw this. Let's get one out of the way. So here's my 5 sectors, 1, 2, 3, 4, 5. I got my graph in the last one. I knew I went around once, and then I landed at 2 pi over 5. All right, so I'm just redrawing this graph here. If I wanted to get a negative coterminal angle, subtracting 1 revolution is not enough. Right, if I subtract 1 revolution from 12 pi over 5, if I take 12 pi over 5 and I subtract 2 pi, because I want to get a negative coterminal angle, so I need to go to the negative direction. If I subtract 2 pi, what does this give me? 2 pi over 5, right? Because you would think of this as 10 pi over 5. And you end up with 2 pi over 5. Or if you're super into diagrams, just count it. 1, 2 pi over 5. But that doesn't give me a negative coterminal angle. I would have to go again to get a negative coterminal angle. Right, so a negative coterminal angle would actually end up going this direction. And in order to get it, you would have to subtract 2 times 2 pi. Right? You'd have to do 12 pi over 5 minus 2 full revolutions. Right? Subtracting 1 revolution is not good enough, so you subtract 2 revolutions. So you would have to calculate 12 pi over 5 minus 4 pi. Or 12 pi over 5 minus 20 pi over 5.
So you just drew 1 revolution, but then you're saying it has 2?
Which is negative 8 pi over 5. One second. So this is my negative coterminal angle. But what I was saying is that subtracting only 1 revolution does not give me a negative answer. So I had to instead go another revolution. I had to subtract 2. How could you tell from the very beginning? Look at this mixed number. This is bigger than 2 pi, right? So subtracting 1 revolution isn't going to work for a negative coterminal angle. So you know right away you're going to have to subtract more than 1 revolution. 2 is enough because this is less than 4 pi. If this were bigger than 4 pi, you'd have to subtract 3 revolutions. What I wanted to warn you about it's really difficult to use mixed numbers if you change signs. See, right here we changed signs. We were positive, we became negative. If I wanted to use mixed numbers to do this, kind of like I did here, it turns a little ugly. Right, if I wanted to try mixed numbers. What I see a lot of the time is I see people saying, well, I have 2 2/5 pi, and I know that I need to subtract 4 pi. Do you know what they tell me? Negative 2 2/5 pi. Right? Just take 2 minus 4, let the 2/5 stroll along. Is that correct? Oh, no, that's very bad. Okay, that's wrong. This is a little bit bigger than 2. This is 2 2/5. Right? Think about it as money, right? If you had $2.40 and you subtract $4, you have negative $1 and how much? 60 cents. Okay. So what I would suggest is if you're going to change sign, don't even try to do it with mixed numbers. Just do improper fractions. Questions? Okay. The last 2 things in this section that aren't specifically related to graphing angles are formulas that might come in handy in your life, at least in your school life. One of them is the arc length formula. So the way arc length works, so an arc is just a portion of a circle. Right? So if you have some circle of radius r, so say I know this distance here is r, then I can calculate the length of an arc from here to wherever I want, as long as I know the angle that sweeps out that arc, which we usually call theta. So this distance here is the length of the arc, and it's called s. In the formula for arc length, the formula for the length of that arc is that s is equal to r times theta. In order for this formula to work, you have to be in radians. This formula is based on radian measure.
I have a question.
Yes.
Which part is the length? Like S or arc length, which part of that is the length? Is it the whole thing or is it just that?
This part.
So it's just-
Is the arc. So the arc is just the piece that's on the circle. And the length of the arc is just the length you would walk along that circle. So if I give you, for example, let me start with the last one. Find the arc length of an arc along a circle of radius 1 intercepted by an angle of 4 pi over 3 radians. So I'm telling you, you have a circle of radius 1. And I want to know what's the length of an arc if the end of the arc is intercepted by a 4 pi over 3 radian angle. So first, just for a picture, where does 4 pi over 3 land? Below the negative x-axis. It's actually in the 3rd quadrant. And if you were going to graph 4 pi over 3 for me, because I'm a super perfectionist when it comes to radians, you would split pi into 3 equal sections, bottom pi and top pi. 1, 2, 3, 4, 5, 6. So the arc I'm talking about starts here, travels all the way around my circle of radius 1 until it gets to the 4 pi over 3 ray. I'm asking you for how far you've gone along S, for what S equals. So I didn't actually give you any units, but your radius is length 1 unit, 1 inch, 1 meter, whatever unit it is. And I want to know how far you've traveled along this. You use the formula r times theta. Since r is 1, you just get 1 times 4 pi over 3. And your arc length is 4 pi over 3. When the circle is radius 1, the arc length and the angle are the same thing. In radians, not in degrees. In degrees, this doesn't work. Okay? But in radians, if your radius is 1, the arc length and the angle are the same thing.
I thought it was the arc length. If the arc length was 1 radian, then the radius would equal the arc length. I mean, I thought if the angle was 1, then the arc length would equal the radius. I think
Well, yeah, I mean, that's true too, right? If this is 1, then this might as well not be here, and the arc length equals the radius. That's true, but it's not really as useful.
Okay, because it just doesn't teach us that method in the book. That's why.
Well, I'm not trying to teach you a method. The method you should use is just use the formula.
Oh.
But yeah, they might make a little bit different association, although I hope not. But what I'm trying to say is whether you are measuring this rotation, right? This rotation we called 4 pi over 3 radians, or whether you're measuring this distance that you walk. Right? 4 pi over 3 meters, or whatever the units are. As long as the radius is 1, these will be the same. And it goes the other way too. If the angle is 1 radian, right, then whatever the radius is will be this distance. That's also true. But what if the radius is not 1 and the angle is not 1? Right? So suppose I do the same example, but I want the radius to be, I don't know, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I give you a radius 10 circle. And I give you 4 pi over 3 again, which we know lands down here. Now my question is, what distance do I walk from here all the way around to here?
40 pi over 6.
What is it?
40 pi over
40 pi over 3. It's just 10 times this angle. Right? Because the radius is 10, so you've gone 10 times as much. So you can use the formula S equals r theta. That's the arc length formula. You know r is 10, you know theta is 4 pi over 3, always in radians. Multiply straight across, you've gone 40 pi over 3 units. Whatever the unit of measurement is. Inches, meters, yards, millimeters. There's another formula they have in there, the area of a sector of a circle. No, I'll give this to you and then I'll take a photo. So a sector, if you have a circle of radius r, let's say this guy has radius r, you want to know the area of some sector, and you happen to know the central angle of the sector, you happen to know this part here, is theta, what do you think the formula for the area of the sector will be?
R squared minus the
R squared minus, no, oh, look here. Here's how I remember it, right? Suppose you had a full circle. Suppose you had a full circle. What's the area of a full circle? Pi r squared, right? Hopefully you remember that from some other class. And what's the central angle in a full circle? How far would you have to go to make a full circle?
360.
Or in radians?
2
pi. So you take this angle here, but you cut it in half, and then you square the radius. That's how you get the form. So over here, it'll be the same thing. It'll be 1/2 your central angle times the radius. What is radius squared for area?